We talked about the fact that since the regression model is a model, it's an estimate, when we calculate a prediction, are we guaranteed to get the exact value that we would get in real life if we did the actual study? No, we wouldn't. Yeah, okay.
Was the linear regressions 3.2?
Section 3.2, yeah.
Well,
Okay. So when we put an x value in to our regression model, we get a y value out, but that y value is a prediction. It is not necessarily going to be the exact value we would see with that given x value in real life. So what we're going to talk about today is how to handle that type of situation. So residuals. A residual is the difference between an actual value and the predicted value. So when we have our scatter plot and we fit a regression line to that scatter plot, does the line pass through every single point in our scatter plot? No. The only way it would is if we happen to have a scatter plot that lined up exactly perfect. Okay? So what we're talking about here is that when we fit that line, the line doesn't even hit the values we currently have. So the points that we actually do know. For this x value, we know we get this y value. Okay? So what's happening is that line's passing through the data. It's giving us an estimate of what we're looking at, but it's going to make some mistakes. It's not going to guess everything exactly like it should. So what a residual does is it tells us how far off our guess actually is. So here's that example from yesterday with the items from Burger King. So we had the amount of protein as X, the amount of fat as Y. Okay? So if we notice, our regression line here in red passes through our scatter plot, but it doesn't hit all the points. Okay? In fact, it hits almost none of them. Okay? So what's happening here is if we were to actually look at some of these specific values, so the values that we actually know, we know that this X value, for instance, would be like 25. Okay? So if we know it has 25 grams of protein, well, we know how much that particular item had as far as fat's concerned. But our line would have predicted a different value. So these residuals tell us the difference between what we know to be true and what the line predicted to be true. So what we're looking at here, and this is important right here, the formula to calculate a residual. You have to know that. That is not something that will be on a formula sheet or anything like that. You have to know it. And the order is important. So you have to know that it's y minus y hat. The y would represent what? The actual y value. The y hat is what the line predicts. So when we're looking at our screenshot over here, our actual value of y happened here. The line predicted that for that value of x, we'd actually get this y value. So if we look at the difference between the two of those, if we take the actual minus the predicted, that's going to give us our residual. How far off were we? Okay? So when we calculate residuals, that's what we're talking about. We're looking at a difference between what actually should happen and what the line predicts to happen. So basically it's just going to indicate to us how far off are we at that particular point. How far off was our model at guessing the correct value. All right. One of the things to keep in mind when working with residuals, if we were to go through this entire scatter plot and calculate every single residual. So if we went through and every single point on the graph here, so for this point, we would mark its residual. So here's my y hat. For this point, we'd go through and mark its residual, and we find all these differences. So we just go through all the different points. Okay? If we were to do that for every single one of our points that we collected, we would expect our residuals to come out to 0. Why would that make sense? Yeah, when we're looking at this now, the line won't necessarily cut exactly half and half, right? There might be some more points above than below, but when we find that that regression line, we're finding, in essence, kind of a mean, an average, right? So we're passing through the averages of those points, essentially. So what should happen is we should have the same distance away from the line above as we have below. And since we're subtracting actual minus predicted every time, some of our residuals will be positive, some will be negative. They should all cancel out because that line should have overestimated as much as it underestimated. If it's in the right spot, those are going to come out to be 0 every time. Okay? So, a couple things about residuals. If we get a negative residual, so the sign of a residual will tell us whether we over or underestimated our actual value. So a negative residual means that the predicted value was higher than the observed. That means we overestimated the actual value. So when you see a negative residual, it meant that we overestimated our actual value. Which means a positive residual would tell us that we underestimated. So if we get a positive residual, that means that my predicted value was less than the observed value. So that time the line underestimated what the value should have been. And like we said, it should be overestimating and us underestimating the same amount throughout the entire scatter plot. Those over and underestimates should come out to cancel each other out if we were to take all of them and put them together. Okay, so negative means overestimate, positive means underestimate. Good there? It is. You'll have to get it later. I'll come back to it. Okay, so negative residual means we overestimate, positive means we underestimate. All right, so one of the things that you're going to be asked to check, and we're going to talk about how to do this on the calculator here a little bit later, residual plots. So we have a scatter plot that relates x to y. So we take the x and y values, we plot them, we look at what relationship they have. A residual plot looks at it a little bit differently. For each value of x, it looks at what the residual for that particular x value came out to be. So we're going to see how the differences come out and relate to x. So we're looking at a scatter plot of the residuals against that x value, that explanatory variable. Now, the reason we look at scatter or the residual plots here is mainly for us to determine if a linear regression model is appropriate or not. One of the things that you can have happen is when you look at a scatter plot, you might look at that scatter plot and say, well, it looks pretty linear. I'm going to fit a line to it. But once you fit that line to it, if you look at the residuals, there are times where those residuals will show some sort of pattern. You're going to see some sort of curve emerge. And that's not a good sign. That means that your scatter plot was not, in fact, linear, which means a linear model may not be appropriate for that particular set of data. Okay? So the residual plots can sometimes tell you things about the association that the scatter plot cannot. So when we look at a residual, when we look at a residual plot, what we're looking for is completely random scatter. So what the calculator is going to show you, or if you were creating a residual plot, you have this value of 0 here, which is representing the actual line. Okay, so that's the actual regression line that we created. Now when we calculate our residuals, we're simply finding a distance from the actual value to that line. So all we're doing here is plotting those distances. So at this point for x, this particular point was lower than the predicted value. So we had a negative residual. So it was down by about maybe negative 0.2 or negative 0.3. This point here was below at almost about negative 2. So it was almost 2 below what our line predicted, and so on. So all it's doing is keeping track of how far the points are from the line and in which direction. Was it over the line or under the line? Was it a positive or negative residual? Okay? So when you look at these residual plots, that's really what it's telling you. Now when you see a residual plot like this means that the regression line would fit the data well. There's no pattern involved in the actual display here. Everything's just randomly scattered around the line. Okay? This is what we want to see when we look at a residual plot. And like I said, when we get some data here in a little bit, we'll do this in the calculator. I'll show you kind of what this looks like. Okay? Now, like I said, there are times where we might look at a scatter plot. We say, okay, it's linear. Let's go ahead and fit a line to it. But when you check your residual plot, something like this might happen. So when we check our residual plot, at low values of x, we were overestimating the value, so our line was predicting higher than our actual values were. For middle range of x values, we were under-predicting, and then at the end, we were over-predicting again. So what's happening here is it's showing us that our initial scatter plot had curve to it. There was a curved relationship to it that we may not have seen in that original graph. So here we have a nonlinear relationship, which means our regression line really isn't going to be useful to us, because we're trying to fit a straight line to a curve. So if you see something like this emerge, where the curve occurs, that means we should not have used a linear model to approximate the relationship. Does that make sense? So any type of pattern that emerges within our residual plot means something bad. It means we can't use our line, or it's not going to be as accurate as we would like it to be.
So when that is the case, then like, if we put an answer for something, then what would our answer be?
Well, what they would ask is something like, they might ask you to predict with the given regression line, which you still do. But if they ask if a linear model is appropriate, you would check the residual plot, and you would say, no, a linear model is not appropriate in this case because there's a curve in that residual plot. So basically with these types of questions, what they're asking is, should we fit a line to this information? So you're going to fit the line to it, check the residual plot. If you get a random scatter, you're good to go. The linear model is appropriate. But if you see any sort of pattern emerge, a curve or anything like that, you would say, no, a linear model is not appropriate, so it's not going to be useful for prediction purposes. Okay? Here's another thing that you might run across. So you see your scatter plot, looks linear, so you create a residual plot just to check and make sure. And what we see is this sort of pattern. Now, do we see any sort of curve? No. So there's no curve that appears, which means we can use a linear model. But notice, while the points are really close to the line to start off with, what's happening as x increases? Yeah, they're starting to spread out more and more. So when something like this is happening, our predictions are becoming less and less accurate as x increases. So this is what we call fanning, when you see it kind of start to spread out, or it could happen in the reverse. Your values of low x's might be really scattered, and then as x increases, it starts to become more and more accurate. Okay? So in these cases, a linear model is still appropriate because there's no curve, so it is linear, but we have to be careful if we're going to be using large values of x, because our predictions are not going to be as accurate. Okay? So basically what you should see when you're looking at a residual plot is a random scatter. Any sort of curve in the residual means we shouldn't be fitting a regression line to our relationship. If it fans, like that last one, we can use the linear regression, but wherever it starts fanning out, whether it's at low x values or high x values, there we have to kind of be careful with taking our predictions because they're going to be less accurate at those points. So when you look at a residual plot, it should be a very boring scatter plot. There should be nothing in it at all. It should just be completely randomly scattered throughout the entire thing. We okay with that? Okay. Next thing, with residuals. So residuals, we're looking at the difference between what we know to be true and what our line predicts to be true. So with that, we can actually calculate a standard deviation for our residuals. Our residuals become their own distribution. So with those types of distributions, we would like to know what our standard deviation is. We want to know how much the residuals spread. How close are our predictions to what we should expect to see? So standard deviation for residuals is generally going to be denoted with an S sub E. That E is sometimes what they use to denote a residual. So back on that first slide, when we wrote out the formula for residual, so residual was equal to y minus y hat, right? In the book or on quizzes or tests or things like that, they might not write out the term residual, they might just use the letter E. So E is going to denote a residual. So when we do the standard deviation for residuals, most of the time you'll see this S sub E. When we talk about tomorrow, we're going to talk about computer outputs. So when you run things through a statistical software on a computer, they have outputs that all kind of look similar. When those come out, usually they're just going to denote standard deviation with just a plain S. And you just have to realize that that's a residual standard deviation because they're running a regression analysis. And we'll talk more about that tomorrow. So E is going to be what we use to denote a residual. SE is going to be what we use to denote a standard deviation. Now, what standard deviation tells us is the typical prediction error. So when you get the standard deviation, what that's telling you is if you use the line to predict. So the way to interpret standard deviation, if we use this line to predict, then you will typically be off by however much your standard deviation is. So if your standard deviation for the residuals was 2.7, what that means is every time you use the line to predict, you can expect to be off by about 2.7 from what it normally would be. So it's telling you typically how far off are you going to be from what you should actually be getting from the line. Okay? We go with standard deviation. So we'll talk about that here in a second. And really, for the most part with standard deviation, I'm not going to ask you to calculate residual standard deviation. The only thing I would ever ask you to do is interpret it. And we're going to go through an example that kind of shows you exactly what that looks like here in a little bit. The other thing that's important when working with regression analysis. So we create our line, we find our correlation, we calculate our residuals, we look at our residual plot to make sure that our linear regression is appropriate. But the other thing we're going to look at is what's called the coefficient of determination. So the coefficient of determination is simply R squared. And what is R? Correlation. So the coefficient of determination, this R squared, is just the correlation squared. You literally take the value for correlation for R and square it. Okay? Now what it does is it tells us the percentage of variation that's accounted for by the model. So we know that the model does not pick up every point exactly. It passes through the middle of the points and the points spread around it. So we have variation within the points. Some are above, some are below. They're kind of all over the place. Hence the name scatter plot. So the R squared tells us how much of that variation gets accounted for in our line. So how well does our line actually describe our data? Okay? So when you're looking at R squared, because it's a percentage, it has to be a value between 0 and 100. It cannot be negative. If you had a negative correlation, when you square it, what's going to happen? It's always going to become positive. So since it's R squared, it's always a positive value. So it's always going to be between 0 and 100%. The higher the percentage, the better fit for our line. So the better our line is going to fit our actual data. So a couple examples here. Just have a couple scatter plots with some regression lines through them. So correlation of 0.994 here. Correlation squared would be this 0.994 squared, which is 988, which is 98.8%. So 98% of the variation in our points is accounted for or picked up by the model. Over in this one, we notice the lines are scattered a little bit more loosely around the line. So we get a lower correlation, 0.932, which leads to a lower correlation squared, 86.9%. So in this particular one, only 86.9% of our variation is picked up in the model. Okay? Now, as far as correlation squared is concerned, if you were asked to calculate correlation squared, how could you do that in your calculator? All right, if you go to that LinReg, so when you actually take your two lists and you go to the LinReg option, so everybody get on your calculators here real quick. Just be sure, go ahead and check your list, make sure you have some data in list 1 and list 2. If you don't have anything in there, just fill some stuff in. Make sure you have the same number of observations in list 1 as you do in list 2, so that they match up. So if you have data in there already, go ahead and go to your stat, over to calculate, go to your LinReg. And so there you have your A, you have your B, right below that's R squared, and then you have R. Okay, so if they ask you to calculate R squared for a particular problem, you can plug the values in, do your LinReg, it's going to be right there. Okay? If they give you an output of some kind and they tell you that the correlation is 0.96, and they say find correlation squared, all you would do is take 0.96 and square it. Right? What if they ask you to come back from correlation squared, though? What if they said, here's your R squared, 98.8%, find the correlation from that? We take the square root. Square root of what, though? The decimal version. Don't take the square root of 98.8. That's a percentage. So we convert it to the decimal part, and then take the square root. Now, when we take the square root, what would we have to account for here? Correlation squared is always positive. Correlation, though, can be positive or negative. So when I take the square root of my correlation squared, what type of value will I always get? It's always going to be a positive number. So how will I determine when it's supposed to be positive and when it's supposed to be negative for my correlation? How will I determine when I use positive and when I use negative? Your scatter plot should tell you. If your scatter plot has a positive association, your correlation should be positive. If your scatter plot has a negative association, your correlation should be negative. So if this was a negative association here, and we do the square root of 0.988, we're going to get a positive 0.994. We'd have to convert that to a negative to match our direction. Okay, so kind of keep that in mind if you're converting between the two. The signs are important. We okay with that? All right. So let's go through a quick example here. This is going to kind of go through everything we just got done talking about. Calculating and interpreting residual, talking about what standard deviation looks like, talking about R squared. So this example, you can just follow along. If you want to have this later on, you can always go online and print these particular slides off the website. Okay? So what we're looking at here, the stats for the relationship between the average number of points scored per game, it's going to be our X value, and the number of wins is going to be our Y value, for the 12 football teams in the SEC. So what they did is they gave us all the information as well as a scatter plot with a least squares regression line fitted to it, and then a residual plot as well. So here we have our scatter plot on the left. It's got a regression line fitted to it. On the right, we have a residual plot. So they calculated the residuals, put it into a plot, and we're looking at that. And then they tell us our regression line, they tell us our standard deviation for the residuals, they tell us our correlation squares. So we have everything we need as far as a regression analysis problem would be concerned. So, using this information, the first thing we want to know, we want to calculate and interpret the residual for South Carolina, who scored 30.1 points per game and had 11 wins. So here is their actual information. They had 30.1 points per game, they had 11 wins. On the scatter plot, I've gone ahead and highlighted. This is where South Carolina would be. Okay? So what we want to know is what is their actual residual. So what would we need to do here? How do I calculate a residual? Take the actual value minus what? The predicted value. So right now, we have the actual value. When they scored 30.1 points, they had 11 wins. Okay, so we know exactly how many wins they had. What we need to figure out is how many wins our line would predict them to win. So we need to figure out how our line would predict. So what would we need to do? Plug in what? Plug 30.1 in for X in our equation. So if we plug 30.1 in for X, our line would predict that if they scored 30.1 points per game, they would have 9.4 wins on the season. Okay, so our line says if you're going to score 30.1 points per game, you're going to get 9.4 wins. So if I want to calculate my residual at this point, what would I do? We would take 11, our actual wins, minus our predicted wins, 9.4, and we get 1.6 wins as our residual. So what does this mean in context? What does this 1.6 wins actually tell us about South Carolina? They did better than predicted. So they scored 30.1 points a game, which our model says means they should have only won 9.4 wins, but they went and won 11. So they won more than we expected, exactly 1.6 more. So what this residual is telling us, South Carolina won 1.6 more games than expected based on the number of points they scored per game. So when you're asked to interpret a residual, this is what you're using. You're saying that, what's that?
How do you calculate prediction?
Through the line. So they gave us the X value and Y value. So here they scored 30.1 points per game. They had 11 wins. And so we're going to use our line here to calculate the predicted value for Y. So we're going to plug 30.1 in for X, multiply it out at the negative 3.75. It's going to give us our predicted value. So we're just plugging into our regression line that they gave us here. So for 30.1 points per game, they actually won 11, but our line says they should have won 9.4.
Where's the negative 3.75 and then the 0.437 come from?
These?
Yeah.
It would come from the actual data. You'd have to type it in and find the slope and the y-intercept from the points. In this particular case, they just told us this is the line.
What's the formula for that? Like, if it doesn't have those numbers in there?
If you had to calculate yourself,
Yeah, what are the formula?
well, what they'd have to do is give you all the points, so they'd have to say for, like, Tennessee, they scored this many, they won this many. For Georgia, and so on, they'd have to give you all those. So if you did the formula, your slope, that's where you have to do that r times sy over sx, and then your y-intercept would be y bar minus slope times x bar.
Yeah.
Which, on a problem like this, I wouldn't recommend going through all that steps. Just plug in your calculator and do that linreg.
Okay.
So if they give you the data, you can plug in your calculator, do linreg, it'll tell you the slope and the y-intercept. So you would get this for your slope, this for your y-intercept that you plug in. Okay? So in this case, they just told us what it is instead of making us find it on our own. Okay? So, finding a residual. They're going to give you an x value with the actual y. You need to use the x to find the predicted y. Once you have the two y values, take actual minus predicted, calculate the residual. And then as far as interpreting it goes, if it's positive, that means they did better than expected. If it was negative, it means they did worse than expected. Okay? So as far as interpreting goes, that's what we're looking at there. So next question. Is a linear model appropriate for these data? So over here, they showed us the scatter plot, and they fit a line to it. Now, no matter what your scatter plot looks like, you can always fit a line to it. Okay? Your calculator, or you can always calculate a regression line. It's always going to pass through. But whether it's appropriate or not is another matter. Whether we should be fitting a line to it is different than can we fit a line to it. So when we look at this, if we want to determine if a linear model is appropriate, what should we look at? We should look at the residual plot. The residual plot will tell us if a linear model is appropriate or not. And how is it going to tell us if it's appropriate or not? If it curves. If we see any sort of curve or pattern, it's not a good fit. We don't want to use a linear relationship for this. But if it's just a random scatter throughout, then we're okay. So if we look at our residual plot over here, do we see any sort of curve or any sort of pattern emerge? No, for the most part, they're scattered kind of all over the place, right? So, because the residual plot doesn't have any actual patterns, we can say that a linear model is appropriate. So because there are no apparent patterns in the residual plot, a linear model is appropriate.
So like if the residual plot was like the fan type, then that wouldn't be okay, right?
Fan's still okay. So you would say because there's no curve, it's okay to use the linear model. But if it fans, you'd want to make a note that, like, if it fans, so if it gets bigger as x increases, you'd say it gets less accurate as x increases. Or if it started off really weak and then came down to strong, you'd say it's really bad in low x values, but really good at high x values. So the fanning, you're still okay with the linear model. It's just you got to be careful with where you're predicting, because they're going to become less accurate.
Since you said that the residuals have to like add up to
Zero.
yeah, isn't it inaccurate since there's like way more on the lower half than the upper half?
Well, but remember, as far as the residuals go, we don't care that there's more points below the line than above the line, as long as the actual differences come out to be the same. So we should have the same distances below as we have distances above.
So let's say it's not though, does that mean it's not appropriate though?
If your residuals come out to anything but zero, that means you probably calculated your line wrong. So if you calculate your line correctly, the residuals will take care of themselves. They'll come out to zero. What you're looking for as far as appropriateness right now is just whether there's a curve or not. So if there's no curve, we're good to go.
If they kind of create a straight line, but like diagonal.
You still wouldn't want to use it then. So that's a pattern that would emerge that we don't want. So that's a good question there. We talked about curves, okay? But he's asking what happens if something like this shows up in the residual plot. Okay? So it's a straight line, but notice there's this pattern that doesn't follow the actual regression line, right? Which means somehow our line passes through but it's not actually following the data like it should. Okay, so even if you find a linear piece like this, any pattern that's not following the line is not good. Okay, so this would not be a good fit if it was doing something like that. Okay, and you'll likely only see that occur if there's like outliers, because the outliers can change that line really bad. So all your data might be going this way, but one outlier might put your line going negative, though it should be going positive. So that's about the only time you see that, but yes, that would be a bad thing. Okay? All right, next thing, interpreting the value of S. So here's our standard deviation for our residuals, 1.24. So think back a couple slides ago. What did we say standard deviation told us?
Spread around the average.
Yeah, the typical prediction error, right? So basically, this standard deviation is telling us about how far off we should be with each of our guesses. So the way to interpret this, if we use this linear model given to us, so if we use this linear model to approximate our values, we will typically be off by about 1.24 wins. So we're typically going to either overestimate or underestimate by about 1.24 wins. Okay? So the standard deviation, and this statement can just be universal. All you got to do is change the context at the end. When we use the linear model, we will typically be off by whatever standard deviation is with units. Okay? Same statement every time.
Will we ever have to calculate standard deviation?
Not for the residuals. Nope. You will not have to calculate standard deviation for residuals. The only thing I'll ever ask you about standard deviation is how do you interpret it. Okay? Last thing then, interpreting the value of correlation squared. So if our correlation squared is 0.88, as they're saying here, when we make our statement about how to interpret, this is what it looks like. So about 88% of the variation in wins is accounted for by our linear model. So by the line they gave us, we can account for 88% of the variation in wins. And again, this is pretty much a universal statement. All you have to do is change context. So whatever your correlation squared comes out to be, you can make it a percentage. About 88% of the variation in Y is accounted for by the linear model. Okay? It's as simple as that. This percent of the variation in Y is accounted for by the linear model. So when they ask you to interpret R squared, that's your blanket statement. Okay? You okay with that? Yeah.
Would that like mean also like 80% or 88% of the like points are on the line, or like?
Not that they're on the line, it's just saying, so with the line passing through here, these points are scattered all over, right? So there's variation between the different points here. What we're saying is this line is passing through in such a way that it's gonna account for a lot of that variation. So it's accounting for some of these points. That's why we're able to use it to predict, is that it's picking up some of the pieces and making it better, kind of thing. Does that make sense a little bit? Okay. All right. Last thing, and this is not something you need to write down or anything like that. It's just the kind of thing to keep in mind as far as whether a regression model is appropriate or whether it's even useful to us. So one of the things that will tell us whether we want to use a regression model for our analysis, like do we actually want to use this line for prediction purposes, is the value of R squared. Okay? So kind of like when correlation, when it was very close to 1 or -1, it meant that it was a very strong association. The values followed really closely to the line. If it was closer to 0, it meant it was a really weak association. The values were starting to spread out quite a bit, or there was no apparent relationship. The same kind of thing happens with R squared. The closer you are to 100%, the stronger your model is. the better at predicting it's going to be. The closer to 0 you are, the less accurate it's going to be. Now, as far as how big should r squared be before you start discounting the model, is kind of a gray area. There's no specific set like saying if you're below 80% for correlation squared, you don't use the model to predict. Okay, there's no certain cutoff. It depends entirely on context and what you're comfortable with using. So when you're looking at this, a good r squared value, obviously the closer to 100% you can get, the better. Okay? Now, the two different types of things that you can deal with, and we're going to talk about these things later on, but scientific experiments, with scientific experiments, we would want a very high correlation squared value. We want somewhere in the 80 to 90% range to use that model to predict values. We want to be somewhere really high up there because of the nature of experiments and what they tell us. For observational studies, they're a little bit looser with what we can accept. And we'll talk about those when we get to them, but for those, you can be somewhere in the 30 to 50% range, and you might still be okay using the model to predict. So when they ask us whether we should use the line to predict or not, you're looking at residual plot. Is there some sort of pattern that emerges, which means a line should not be used anyway? But you can also look at your r squared coefficient. If r squared is high, yeah, we can use it because it's going to predict pretty accurately. If r squared is low, well, we may not be as comfortable using those predictions because they might not be as accurate as they could be. Okay? So that's just kind of something to keep in mind with correlation squared there. So here's your assignment.